Hi guys, so today we will do some extra topics on sequences, subsequences. Actually, subsequences is a very important topic because there are inner part subset of a sequence having almost the same property of the sequence, so they help to recognize the sequences well. And studying the theory of subsequences we will later on see, and I will also mention now that subsequences actually tell that the limit of a sequence when it doesn't exist. So it's nice, actually very nice. So first we will start. We will revise some basic limits. Okay, limit n tends to infinity. So I like limit n tends to infinity as a LT. Okay. LT n tends to infinity 1 by is equal to 0 where p is greater than 0. Next is and then comes this is the representative version. I am just writing it in another way. Then another thing is a very important one. So we have provided the proof of these later on in the previous video in the description section, so you can also see them, or you can try yourself and leave the proof in the comment section. This one and another one is limit. This one is important actually. C to the power 1 by n is equal to 1, where for all c greater than 0. So these conditions are actually very important, so please pause the video and take them down so that you can and these are the important. So we will see some of the proofs by some other results, and what we will be doing today is it's very important for the further use. And first we will do some basic limits and some results including polynomials of the limits of the polynomials rather. So I'm wrapping the off. So we have some interesting things: algebra of limits, order of limits. So which we have stated earlier in the previous slide, and some basic results that we have stated. Now using this and various combinations of this, we can get to use to know whether some functions like I have given the example 3n minus 1 by 4n minus 7 converges to 3 by 4 actually by dividing by n on both sides. So there is an important step, and we will actually generalize it for any polynomial by polynomial form. So I will state some examples. First example, suppose limit n tends to infinity n square plus 1 by 3n square minus 1. So see, doing the same thing, you just divide it by n square. I am writing it formally, don't do it follow the steps, writing down the answer formally. So I am doing it informally. So it's like it's 1 by 3 because this term will go to 0. Because this is not equal to 0, so this term will go to 1/3, 3, this term will go to 1. So by the algebra of the division property, this term goes to 1/3. So these are the basic things, and see how this algebra makes a certain algebraic structure. I mean a set of objects which we can see using that 1 by n result goes to 0 as I tested. So now we will do something called but I mean we'll do something when limit of a sequence when is infinity plus minus infinity. So limit of a sequence is infinity definition is for all, I have introduced notion in the previous videos, for all positive numbers v greater than 0 if there exists a natural number n depending on this b such that for all n greater than or equal to this, if n is a sequence is greater than b. Simple, see. And similarly for the negative plus infinity and for minus infinity, for all negative number, for all positive numbers b there exists natural number b such that minus of n, and also you can in different way you can write you can take that 7 and you take this c to be less than 0 and see this stuff. So these are the basic things and these are very important actually. So now I will see, I am giving an example. So n, see it grows on and on. I mean it's unbounded because and it's increasing, right? So we'll also see this stuffs again. So mainly it's increasing and it will go to infinity as intensity infinity can be seen from the definition, from the definitions of the function only. So these are the this one is the basic one, is this basic example. Now we are doing this. Now we come to some real examples of sequences, I mean convergence. I will do today some convergence of sequence polynomial by form. This one is very important example and we this will cover actually it is actually the polynomial, okay, by polynomial form. So actually the most important fact is when you write a polynomial, it's of the form, right, a n whole to the power x to the power n polynomial of x x to the power k suppose plus dot 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 a k whole to the power. So right here polynomial of n is looks like a of k whole to the n to the k plus a of k minus 1 whole to the power n to the power k minus 1 and last a of 1 into n plus a of 0, and similarly q of n let be k into the power let the degree be at this k1 and this k2. b1n plus bc. Now actually see one thing, first I have told the convergence of a function actually depends how it behaves at infinity, right? So this will be actually a very important step in understanding why this limit is something that you are going to see. See, the polynomial at infinity is mainly concentrated on this thing, on these two facts, this thing and this thing, because as n tends to infinity n to the power k1 by n to the power k1 minus 1 and all those subsequent terms is negligible with respect to this, and similarly with respect to this. So I mean 1000 to the power 5 is very large than 1000 to the power 4. Right? There is a 3 more zeros. See, n infinity. So when you n grows larger, so difference is making bigger and bigger. So actually you will see that only these two terms will matter, and I will give you the proof why these two terms will matter. So just assume that Okay, neglect the so put in those values of n where n is not in q of n is not 0. So I can write this only when, so these are valid for n which is not 0 and which for which qn is not 0, and we consider all those n's, and as qn is of degree k2, is number of such n's are finite, so we take all those n's, consider n for example such that it's a maximum of the roots of qn. So and consider n in such fact so that it doesn't become 0. So think in that process only. So now I will write it here. Now we will write this Pn by Qn k into the power k1 and all the subsequent stuffs by now see one thing, divide, see whether k1 is greater than k2. So there are two cases actually. So see this case. See whether k1 is greater than k2, or k1 equal to k2, or k1 less than k2. Consider this only. Now it will turn out. Now see, it's very easy. So divide the maximum, okay, over all the sides. I mean, why we are dividing by the maximum? So here we divide by the n by k, and so this can be written as, so dividing by n to the power k1. I mean all these powers. So write it like this. So দেখো দেখা যাচ্ছে কিনা, এই জায়গাটা দেখা যাচ্ছে না, দেখা যাচ্ছে মানে লেখাটা দেখা যাচ্ছে 1/n দেখা যাচ্ছে। আরে এইটা আমার লেখা পড়ছে। দেখা যাচ্ছে দেখ, and see all the subsequent terms will be by 1 by some whole to the power k. So using that thing, all those terms, using that result or first result that I have said in the today's first part, that all subsequent terms will go to the 0, and similarly deleting this. Similarly, all these subsequent terms will go to 0. এবার লেখা পড়ছে না কোনোটাতে। এই লেখা পড়ছে না কোনোটাতে। কাটা আজকে কাটা দাদা। আরে পেন ছিল না? The p by q must be equal to like this. Plus some term which is 1 by n into something, and that term will go to 0, this term will also go to 0, and the remaining part will go to 0 into the thing that is multiplied with, I mean that we divided with common, we took common, right, into the power. Now see, so this term will also go to 0. So for k1 greater than k2, this is constant, but this thing is going to infinity, right? So the limit is infinity. So for k1 equal to k2, it is beautifully equal to the coefficient of the ratio of the coefficient of the first terms, and for k1 less than k2, it will be going to 0, right? 0 into constant is 0. So this is the thing, I mean, where k1 is equal to degree of p and k2 is degree of q. Now this, please note this down, it's very important. I mean, when the degree of the upper thing is greater, it is going to infinity because it is blasting off more quickly than this. When degree of this thing is lower, it is blasting off more quickly than the lower term, so it becoming 0. And when the degree is equal, then the rate at the dominating term, see, it implies that the dominating term is, oh, you have seen on the board, it's written monotone convergence theorem. So it's a theorem regarding how it's a behavior of a certain specialty of function, special type of function. It's a monotone function, a monotone sequence actually. So it tells that the monotone sequences actually converges and if they are bounded. So first we will tell. So first let us define monotone sequences. So sequence is monotonic if I mean, for example, n equal to n is monotone, and I am sorry, I am wrong. It's increasing. I mean, monotone are of two types. That if n is greater than equal to n for all n, then n is called increasing, and for decreasing for decreases, right? So it's simple and enough. So now for monotone convergence theorem, it states that if a sequence n is bounded and monotone, then it converges. So let's see. So first of all, these two things are equally important. A sequence if monotone may not be bounded, and they're necessary actually, but not sufficient. I mean, they are not if and only if converge. If they hold, then it converges, but if they are convergent, then it doesn't imply this. So take an example. Suppose n is monotone, but so we have seen that this limit goes to plus infinity, and I will give an example of a bounded sequence. It's not convergent. For example, sequence is 1 1 1 0 1 0 1 0, this sequence. So see, it currently occurs, and see, it doesn't have any limit, so it's not convergent. So now for monotone bounded sequence, it converges, and now we'll see to what limit it converges. Actually, to the limit it converges, it's not, it's not formally done in this lecture course, but it's how it is. So take the 1 by n. Yeah. So 1 by n thing, see, 0 is the limit, right? And it's 1 by n is bounded, is an example of this monotone. And it converges to 0. So why 0? What is the speciality of 0? That's we are going to see here. 0 is a number. Now consider the bounds, right? N is bounded here. 1 by n is bounded by 0. It is a lower bound, right? And it is greater than 1, less than 1. So lower bound, and see, 0 is, consider any positive number greater than 0. There will be a negative number, positive number greater than 0. There will be a negative number such that, take a positive number epsilon greater than 0. Then there will be a n such that n is greater than 1 by epsilon. So it implies that 1 by n is, n is less than 1 by epsilon. So n is greater than 1 by epsilon. There will, if taken epsilon, so there will be a number here. So for any epsilon greater than 0, there will be a number 1 by n. They have an integer, so that's the definition of limit, right? So that it is in between 0 and epsilon. So there's an integer, right? So now see, this is a property of 0 only. If you take any lower bounds other than 0, say -1 is also a lower bound, but there are plenty there. It will not have this property. Take any number greater than 0, greater than -1, and it will lie in that interval, and it's not true. So this kind of thing actually has special name. So 0 is the lower bound, and actually 0 is like the minimum of the sequence, but the minimum doesn't occur. And actually 0 is the maximum of all lower bounds, and its fancy name is given. It's called infimum, in short INF. So 0 is like a sort of maximum, and maximum of all lower bounds, and it's actually very interesting that 0 converges here. And it's only for monotone sequence mainly. Monotone sequence have this property, and that it converges to the infimum. Monotone bounded sequence, if it is decreasing, and if it is increasing consequently like this, it will converge to the same, like the opposite thing of infimum must be supremum, that is the lowest upper bound, lowest upper bound, that's supremum. So n converges to infimum of n if it is bounded. If this infimum is only property, it is bounded. it is the only property of the monotone. If it is monotone, okay, it's the only property of the monotone sequence, not others. So if it is decreasing and supremum of n if it is increasing, so this is a monotone convergence theorem. It converges to. That's it for the monotone convergence sequence. Now comes the subsequence part. Now subsequence is an important, subsequences are a subset of sequences, infinite subsets of sequences. So why do study them? It's a natural process in mathematical research that we study subsets of a structure, algebraic structure, to know the better properties of it. For example, we will see that the limit of convergence of a sequence usually dependent how about the convergence of the subsequences. For example, we will do this now, that a subsequent, if a sequence converges, then subsequence will also converge the same limit, but the opposite is not true. So let us first define what a subsequence is. To take a sequence an, it's like a1, a2, a3, and dot dot dot, and take randomly, and take any first number b1 equal to a of n1 of this, and define it as a subsequence. So define it the first term of the new sequence, b2 is equal to n. These are the indices of any number from this. Ni's are belongs to greater than equal to 1, greater than equal to natural number. So this is the subsequence of this sequence. This is called the subsequence. So similarly, bn is called subsequence. So either infinitely many subsequences, right? And for example, an is equal to 1 by n, and this is the most marquee example, important example we have been using from the from the beginning. So take bn equal to 1 by n square. So it's a subsequence, and we also see we have done that 1 by n to the power p. For p integers it converges. It will converge, and we'll see why, actually, because it's a subsequence. Yeah, that's true. So for we will do this result. If sequence n converges to L, then subsequence of n, let's define it to a bn, also converges to L. And this is very easy to see if you draw the geometry. Draw the L and take any epsilon greater than 0. That's the main step for every proving of convergence to a limit. So for every epsilon, we know that for this epsilon there is a n of epsilon, for which n minus L is less than, for all n greater than equal to n of epsilon, n minus L is less than n minus L is modulus by 2, distance is less than this. Now see, as the sequence is infinite, the number of terms in a subsequence is infinite, so if we fix this epsilon, so there must exist a number n1 of epsilon which is above this n of epsilon, for that epsilon, which is the number of this subsequence. After this n of epsilon, all the terms of the sequence n will lie in this strip, and consider the first number of the subsequence. Suppose this n of epsilon equal to 5, and the subsequence we have taken, suppose it's a1, a3, a4, a7. So consider this a7. Okay, so for all the numbers after that a7, so 7 and 8 and all those subsequences terms, so all those will also lie in this strip. So there also exists n1 of epsilon, which lie after for all n that bn minus l also less than epsilon. So yes, voila, we have found that enough in one of epsilon that required natural number, and this tells that the subsequence converges to the same limit. You can also see it formally. I mean, we have done it formally actually. So you can see the full description in the full proof in the description. Now after this, we will move on to one of the most important property called that bounded sequence always has a monotone subsequence. It's one of the most important property, and it will lead to one of the most important result in the sequence called Bolzano-Weierstrass theorem. So in the next video we will do this theorem. Every bounded sequence has a as a monotone subsequence. See, bounded sequence may not be convergent, but still it is a monotone subsequence. For example, in give I 1 0 0 1 1 0 1. This example, see 0 0 0 is a subsequence which is monotone and it converges and monotone. And see later Bolzano-Weierstrass theorem states that any bounded sequence has a convergent subsequence. So if we prove this, it means that every bounded sequence is a monotone subsequence. And we also proved in the monotone convergence theorem that any monotone bounded sequence also converges. So it proves that any bounded sequence has a convergent subsequence, and that's a statement of the Bolzano-Weierstrass theorem. And this is the main part of the Bolzano-Weierstrass theorem. It's a beautiful proof given in two books called Shohra Basic Real Analysis and Kenneth Ross Real Analysis. So you can also look up there, or you can see this video and see the proof. Or so please like our video and subscribe to our channel. Happy learning.